Question 14. So we have a right angled triangle and we're trying to prove that the area of these three regions are linked by the equation below. You can imagine that this is going to be a Pythagoras question and you'd be writing that. If I label the sides according to the letter which is the semicircle attached to them, I can see that b squared plus c squared equals a squared. Quoting Pythagoras, using Pythagoras theorem gets you your first mark here. Now, it's worth pointing out that the area of each semicircle is going to be half pi times the radius squared. Now the radius of each of these circles is half of the side length of the triangle. So the area of A is half pi, half because it's half of the circle, pi times the radius A over 2 squared, which is half pi times A squared over 4, which simplifies to 1/6 pi A squared. In a similar way, we can say that the area of B is half pi times B over 2 squared, which, if you follow the same logic, is 1/6 pi B squared, and therefore by the same logic, the area of C is 1/6 pi C squared. Now, if I know that A squared plus B squared equals C squared, I'm trying to show that the area of the three regions is equal to each other. So if I do the area of B plus the area of C, the area of B plus the area of C is 1/6 pi B squared plus 1/6 pi C squared. I can take 1/6 pi out as a factor, as a common factor. So 1/6 pi lots of B squared plus C squared. Now B squared plus C squared I have as equal to A squared. So I can substitute B squared plus C squared as A squared. So this is the same as 1/6 pi A squared, which we calculated earlier is in fact the area of region A. Therefore, this is true. So you get one mark, as I said, for using Pythagoras theorem, 1 mark for correctly getting areas of semicircles, and then 1 mark for showing that it is true.